what you're preparing for and why you want feedback for this.
Oh, sure. Okay, so the reason I'm doing this is because I have an Incur presentation coming up next month.
Incur does not mean anything to most of us.
I'm sorry. There's a national conference for undergraduate research that's coming to Memphis. It's a very large colloquium, I guess, for just undergraduates in general. And I'm presenting a study of human problem solving using the LIDA model and I'll kind of outline what I'm doing today. This is kind of a preliminary look at what I would be doing.
What's the date of the talk?
Of the
Incur.
Oh, April 6th, I think. It's coming up soon, so less than a month. And so I would really appreciate any feedback, criticism. Just start yelling at me at any point during the presentation. That'd be greatly appreciated. So it's an outline of human problem solving. Again. So first we'll outline the outline. I want to go over sort of an introduction of substitution ciphers, and then the more specific cryptocrypt, followed by a comparison of how a human solves problems with how our agent will. And then we'll go more into detail with that, and then a review. And so, in order to sort of determine how humans solve problems, a subset of that would be how humans solve puzzles. And in order to do that, we're going to model a agent solving a simple puzzle, and that would be cryptocrypt.
And a complex puzzle might be?
A medical diagnosis, things like that.
Oh, good, okay.
Which
Yes,
is the end goal.
well, not the
Medical
end goal,
agent X, I think most people are familiar with. Is that true?
Huh?
Are most people familiar with medical agent X in the room?
Oh, I haven't talked to them nearly enough about it.
Oh, I see. Okay, so substitution ciphers in general are small or simple puzzles where.
Okay, here's your first criticism.
Okay.
It's too small. Kids can't.
I should have told him
Now,
that this morning.
It may be better, and it would do better.
Is that a little better?
Yeah.
Oop, there it goes. Okay, let me see if there's anything we're missing. Yeah, no. Okay, I'll have to zoom in a little bit.
Yeah.
So, a substitution cipher is where you have some sort of plain text, some sort of message, and you substitute every letter with a different letter, and then you encode your message as ciphertext. And you can see that right here, where the key is H, T, K, C, etc. Okay, so a cryptogram is specifically a type of puzzle where, well, this is an example of a cryptogram. It's specifically a type of puzzle where every letter is replaced with a different letter. There are other types of substitution ciphers where, for example, all the letters are shifted to a certain like a certain number of letters, so A goes to B, B goes to C, etc. And there are many others that I guess I don't need to go into. So outside of this, we're going to do a two-column comparison of the agent and the human to try to outline the differences as well as clarify, just so that
Chandler,
it's easy. Yes.
here's a suggestion that I use. I try not to put full sentences on the thing, but just phrases, and talk from the phrases rather than from the sentences. And my rule is But if I put a sentence up, I read it.
Okay.
Now, you don't have to follow my rules, and lots of people don't, and you may get other things.
Sure. I'm just gonna.
But
Take
I
notes.
I avoid a full sentence whenever I can.
Okay. All right. Thank
The
you.
the rest of us had the opportunity to learn these things in control of autonomous agents,
Ah, that's right.
but he no longer teaches that, so take note.
Okay.
Yeah.
Sure. So comparing humans and agents is important so that we don't get confused when talking about one versus the other. So I'm just going to kind of go through a simplified version of the LIDA cycle that we'll be using when developing the agent, and the differences between the agent and how a human problem solver might use this. So for sensory input, sensory information in a human problem solver would be read in through some sort of sensory apparatus. So a human will use his eyes to look at a cryptoquip, and over one saccade, you might be able to see one little letter, one little word, one little phrase.
Am I supposed to know what a cryptoquip is?
A cryptoquip is a type of puzzle.
It's a cryptogram.
Oh, I'm sorry.
And actually, cryptogram is probably a better word, because cryptoquip is sort of almost like a brand name of the puzzle that they print in the newspapers that has a little quip that's encoded in a cryptogram. So a cryptogram solving is probably more accessible. But yeah, it's think of it as synonymous as cryptogram.
But I don't know what a cryptogram is either.
Okay.
Oh, he had a slide on that.
Well, here, this would be an example of a cryptogram.
Well, what part of that is a cryptogram?
Where
That's my point.
The very bottom part, the ciphertext.
so
So I think you explained really well the substitution cipher, what that is.
Yeah,
But maybe what you need to do is say, okay, for this particular puzzle, you're given the ciphertext and you have to work backwards to
Okay.
the plain text.
which I didn't hear.
sure.
Yeah, we didn't explain, yeah, it wasn't explained well, I didn't.
Okay.
So what you're given is the ciphertext,
Right.
and the ciphertext is the cryptogram.
Right. And from there, you have to use context clues to try to determine what the plain text is.
Uh-huh.
You are not given the key.
Sometimes you're given a hint. In the newspaper, you're given a hint of one letter, for instance,
So E
R
is equal to
equals
U.
T or something, yeah.
And from there, you can try to solve the puzzle.
Okay,
And I apologize, I use cryptogram and cryptoquip interchangeably. I may continue to do that. Alright, so can you see this, by the way? Is this large enough text? Yeah, okay. So for sensory input, for just a general mind, according to LIDA, sensory information will go in through sensory memory, through some sort of apparatus, like your eyes. And for humans specifically, we'll be able to read in some sort of small image over one saccade. And then the information you receive will be affected by various environmental factors. So light, how large the font size is, where you are in relation to the puzzle, things like that. And we don't need to represent this in our agent, as far as I know, because I don't think it will be
It's not your
necessary.
focus.
Right. I think that's going too deep into it. And as well as doing this, we're going to sort of propose that one saccade is one cycle, such that,
I'm having a little trouble.
sure.
you really think that a human can go through one of these ciphertext in a single saccade?
No, not at all. But, here, let me go back. So if you were given this ciphertext, right? SURRZ, you may see in one saccade SURZ. And just that first set of characters,
SURRZ. See
Right.
that first one?
Yeah,
just that first set of characters would go into your sensory memory, and you would run with that. Or maybe just the first letter, it
yeah.
depends.
something.
Uh,
Okay.
And it would, in a human case, it would depend on font size and how close it was and all kinds of factors.
And you would eventually be able to solve the whole puzzle over several continuous cycles.
More than several. At least,
Okay.
I don't know, if you're really
Oh.
good, maybe.
Yeah,
So
3 or
just-
4.
Just so I'm clear, are you trying to model, so in any given sensory sampling, however you want to call it, what are you pulling in with your sensor, and are you actually modeling something like a saccade, or are you just taking the current puzzle state and going with that in one input?
The,
Yeah.
so the input that's going into sensory memory is going to be something like a saccade. It'll be just one section of the total input.
Okay, so you are going to be merging, so you're not going to get the entire puzzle state in one sampling of the environment. You're going to have to integrate
Right.
multiple samplings of the environment to get the entire puzzle state.
It's gonna be something like a sliding window.
Okay.
Yeah,
Yeah.
that's a
And,
good
and
example.
so saccade, yeah, I mean,
Okay, go ahead.
Sure. Okay. So, leaving sensory memory, we go into perceptual associative memory. In a human puzzle solver, you would have a sort of conversion from the image that you received from your retina to a more of a lexical token, some sort of concept of what the word is, of what the string of letters is, and you would also have some sort of semantic interpretation of that as well. In our CryptoQuip agent, something similar would take place. You would read in the image and interpret that as a series of characters. However, you would have a maximum token length, so I don't think that if we were to go back to this one more time, I don't think that if I was to look at that, the key, HTK, CU, etc., that I could see that entire string in one saccade. So there would be some sort of maximum length. Oops. And in addition to that, Steve has proposed some sort of semantic portion to Pam, but I'm not really sure what. I kind of wanted to get the group's opinion on that, on
what?
how semantic how a semantic portion to Pam would work, I guess.
So when you say that, so it seems like you could break this up into, so you're saying lexical token, and by lexical token right now, you mean some string of letters.
Yep.
Of some length. Now, you would recognize each one of those individual letters as an individual element inside of Pam, right? When you recognize A, you recognize B as components of this lexical token.
and the lexical token itself would have a PAM node of some sort associated with it for the purpose, at least of one of these blank nodes, it's a thing. You know, we're looking at it as a thing, or it's a word, an unknown word. Perhaps it would be, you know, I don't know. It's got to be. That's the token. Is the whole thing.
Yeah. So yeah, I think from what we said last time, you definitely would have to have a blank node for that whole thing. And the question is, would you actually learn that back into PAM, or would it be divided up into?
We're not going to model learning, but we can't talk about learning on the human side of,
Right.
of the thing.
Yeah, all I was thinking is that, would Pam know about, you know, LZU or whatever, SZRRU?
No.
Or would Pam just know about A, B, C, D, and then the actual words that could potentially, I'm just trying to figure out would be recognized in Pam. It
If you're
seems,
gonna have a LIDA agent, and if it's gonna see these 3 letters or what, then you're gonna need, it's gonna have to put a node into PAM, isn't it?
Yes.
For that.
Right.
And that's learning, isn't it?
Okay. Well, I don't know if the node has to be in a PAM. If it's just a blank node that has some sensory content associated with it or some letters associated with it, and it goes into the workspace, I don't know that
But you may have to come back and forth with it too.
we might not be able to do it without some kind of learning. But we want to minimize the complexity of the
But
software agent.
the complexity of the learning is gonna be, very simple, no
Okay.
matter what, because the problem is simple.
Well, in the human case,
The environment is simple.
in the
Not
human case,
the problem is simple, the environment is simple.
yes. So the human case, the learning can be complex, I think,
Well,
because
that may be, but
Yeah.
but
and see, there's an intermediate state when you're solving these. When I work them, especially the ones in the paper, you know, if I decide that if I think that M is an E, then I'll write E above all the M's in the puzzle, and so that'll be part of my input. You know, that I know that the E, and so then in my mind I'm combining that with what the coded text is with an E in that position. So I could have a lexical input that is partially unsolved letters and partially solved letters, and that could cue in PAM a word that I know, and I see C and an unsolved letter and a T, and I'm thinking, oh, that could be cat or cut or, you know, and so that's what I'm calling a semantic association for the lexical token. And
got it.
and there's got to be something of that, because you can't know that the puzzle is solved unless you're recognizing, oh, this is a word and that's a word, so, you know,
Yes.
so that's got to happen somehow. Does that make any better sense than what we talked about this morning, or?
I think so. I think we should talk about it more after
Okay.
this.
Oh, let me get back to one other thing. In here, it's perfectly reasonable to go from slide to slide and never talk about what perceptual associative memory is. But if you're out there talking to that group, you're gonna have to say what,
Oh, right, yeah, I've been kind of glossing over
yeah,
it just
and that's
because.
fine.
But no, it's good for him to bring it up, because you're going to have a lot of things to remember, and if you forget that one, you're going to be sorry.
Yeah,
That's true.
yeah.
No, I've had that happen before in talks. Okay, so next in the workspace, a more elaborate comparison, and I think, no, it wasn't here. Okay, so on the workspace, a few comparisons. Structure building codelets in a human agent, you would have, if I was solving a puzzle, I would have structure building codelets that were generated dynamically, sort of methods for solving that are generated dynamically. Whereas in our cryptocrypt agent solver, we would predefine ways for it to substitute one letter with another, substitute one word with another, things like that. However, they would build the options, the specific options for each individual cryptocrypt dynamically. That wouldn't be coded in. So in terms of attention codelets, it would act the same as it would in mind, as far as I can tell.
Well, I think there may be some complexity in the human case that we're not going to model, at least on the first pass. Has anybody got any ideas about how the attention codelets work? Because Chandler and I talked about this morning, and I could not do anything other than be very vague about the way the attention codelets are going to build coalitions and compete for them to come to consciousness in a case like this. Is it just the option with the highest activation, or is there something more complex that could happen?
It seems like if you recognize a word or something else that has a higher, whatever, I don't want to say, if it constrains the puzzle more, meaning if you say, okay, well, it looks like, some 6-letter word could fit nicely into here, it seems like that should be given some priority over just, well, maybe I should try Z in this position because of some frequency analysis, I don't know.
Yeah, well, that's related to another question we had. How, obviously the different options are going to compete by means of some activation. Who's going to assign that activation? How's it going to get calculated? Is the structure building codelet going to calculate it when it builds it? Is there going to be some other type of codelet for doing that, or the attention codelets have something to say about that? I know the attention codelets want to, in the human case, we may not model that complexity over in the agent, but in the human case, the attention codelets want to put content together that can go together in order to raise the activation and increase the chances for selection, I think.
I'm sorry, who should do this?
Attention codelets, building coalitions. Building coalitions that will have higher activation than the uncoalitioned,
But the attention codelet
unallied.
has this concern that it's interested in.
Yeah.
And if it starts putting things together to get more activation, it may at the same time get further away from its concern, which would reduce its activation.
So that's a trade-off.
So that's a trade-off.
Can you give us an example? Maybe if you could do it in this context, that would be great. Can you give us an example of such a concern? Can you do it in another context? So you don't know what you mean?
I know what I mean,
But
at an abstract level.
okay. So you can't make it any more concrete?
I don't think so.
Would the concerns be predefined?
Every attention codelet has a concern. Now, the original, when you first begin with an agent, you've got to have some predefined attention codelets. Those concerns are predefined. Then, when you learn new attention codelets, that learning process will add things or subtract things from concerns. So they're not predefined, but they are learned. But any given attention codelet, its concern is there, and it's fixed.
Okay.
So, and the act, Steve, as far as who's putting the activation in, I think that the activation of a structure that's built needs to be done by the structure building codelet.
Okay.
I think he needs to do that.
Now there could be other things that the structure building codelet doesn't know about that might later affect the activation.
Well, we've also talked about the activation of the coalition, and the coalition's activation needs to be done by the attention codelet. Who builds the coalition.
So novelty, for example, is that one possible concern where we have a structure building codelet, we've got this blank node that gets created, it's not being recognized what that content is. The attention codelet is concerned with novelty, it's able to determine novelty based upon that structure.
That's a great possible example. Does that work with your model, Stan? What he's saying is that, okay, there's an attention codelet whose job is to
bring new things.
Well, it's to recognize content that doesn't cube ham, which means I don't know what that is, and then try to bring that to consciousness. Is that an example of a concrete concern for an attention codelet?
Sure, I would think so.
That's a great example.
Now, whether or not you might have to build that in to begin with, and make that.
I would think so.
Yeah, I can't see how you'd learn that.
And there'd be some sort of parameter to tune that, because different organisms might have different.
You might be able to tune it if you put in one version. You might be able to tweak it.
If you're too concerned with novelty, you might die, and if you're not concerned enough, you might die. So,
So what, just to help my understanding on this as well, to continue the example. So once this attention codelet has identified this concern of novelty, this thing is now, a coalition goes over to the global workspace to compete. What is it, in this case, that's making it more attractive in the global workspace? Is it the activation that the attention codelet is?
Activation's all it competes on.
So what is it? So I think that the structure building codelets, they have some base level activation, there's some current activation. I'm sure the attention codelets probably give some kind of activation based upon how relevant they are.
You're saying, what you're really concerned with is how does the coalition get its activation? All right, the coalition first thing has a certain structure that's put into it. That structure brings with it an activation.
Okay, so that activation is coming from, in this case, the blank node and
Okay.
whatever the structure building codelet did, right?
Yeah,
That's one factor,
Okay.
is the activation of the structure itself. Yet a second factor is how close that structure is to the concern of the attention codelet. If it hits right on top of it, then you multiply, you have a factor. You know, the further away it gets, the lower the factor that the multiplier is. Then you also have to take into account the activation of the attention codelet itself. What it is, it will have had a base level activation depending upon its usefulness in the past. That's one of the factors. And then there's the fourth factor that has to do with the locus coeruleus.
Okay, is this in Tamash's paper?
This is all in Tamash's paper.
Which paper is it?
It's in the paper about the attentional blink.
Okay.
And
Oh.
Tamash's paper about the attentional blink.
That reminds me, that paper that I was trying to find that you presented last time, Chandler, there's some stuff in there that we want to look at. So make sure, I just want to put, while I'm thinking of it, the talk that Sean gave last week, that I've got the YouTube videos, you need to, at some point, look at them, you know, and maybe look at the paper.
I think it's 2010 sensory and perceptual
Which-
scene or something of that
which
nature. On our site. On our
Yes,
site.
which hasn't been published,
Right.
and there's a doc version of it on our site.
Oh, sure.
And this is another one that we need to look at, is Tamash's paper on attention codelets, because, okay. Attentional blink. Link. Okay, 2012.
You said it was called what?
I think it's called sensory and perceptual scene, something of that nature. It's 2010.
And it's,
It's Ryan and Javier and Stan are the authors on that one. I think it was for the Flares, maybe?
in the Journal of Cognitive Systems,
Or Journal of
McCall,
Cognitive
Snyder, and
Systems.
Franklin, 2010, Sensory and Perceptual Scene Representation.
Is the Flares one the grounding one? What was
Yeah.
Flares? Is that what it was the other?
And then the other one is 2012, a LIDA-based model of the attentional blink. So, anyway.
Go ahead.
All right, and the third portion to the workspace comparison was cognitive content, where which consists of items coming from Pam as well as just items coming from Pam. So that would be things like wanting to set X to Y and unsetting X and updating the puzzle. And in our model, the only main difference is that for simplicity, we'll set the agent to want to update the puzzle over one cycle instantaneously rather than doing something such as, like, once you realize you want to change M to E, looking at the puzzle, going through the entire puzzle, marking out M, writing E above it. I don't really know if having an instantaneous update will change the final outcome at all.
Well, it'll change the final outcome if what you wanted to do was to mimic a human doing it, because you get the timing off.
Okay.
But that's may not be what you want to do. See, very often we're building agents in order to simulate human data on an experiment. But that's not what you're doing here.
Yeah, we do want to simulate workspace dynamics to an extent,
Yeah,
but
but
there's
not
some
experimental data.
correct.
Yeah.
Okay.
I have one little
Sure.
comment on the structural decoded. So when you're comparing generated dynamically in humans versus predefined in this agent, because structural building correlates are so important, if you just create that distinction that in humans all of the structural building correlates are generated dynamically versus you are doing all of them predefined, that to me gave a perception that your agent is too far removed from realistic or human-like agent. To maybe just to make it more more closer, you can say that those predefined ones that you have are something very similar to ones that would be there in humans as well, but humans can learn more and have more of them by solving more puzzles. They can generate more dynamically, but the predefined ones would, if you can make that claim, I'm not sure if you can, but if you can make that claim, that predefined ones that you have would also exist in humans.
Yeah, it's sort of an interesting problem about which structure building codelets would come predefined and which ones are learned. And it's something that we've talked about quite a bit, Stan and I, and it's not, I don't think we have a good notion at this point which ones are the predefined ones that you just come with and which are learned. But I would think certainly some of the stuff that you're doing here is, you know, you're doing lexical processing, and I would assume that those things would certainly, well, you know, are potentially learned in humans. That lexical processors, structural building codes that do that would be learned.
But with regards to your idea, Poulin, I think that's what we're thinking. For simplicity's sake, we're trying to pick a couple of ones that seem to be common and very useful for humans.
Yes, that's
And so to predefine a subset of ones that humans do, like one of the main ones that I do is to look for the shortest word that's in the puzzle, and like, you know, 2 or 3 letters, and then think of all of the words that I can that have 3 letters, and if there's a clue already, like if it's 3 letters and it ends in E, you know, are the first 2 letters the same or are they different, you know, and if they're different, if all 3 are different, then I think I'll try the, because that's the most common word. And so